Hello and welcome. Let's look at some application problems of exponential functions. So the first one we're going to look at is financial application, compound interest. Okay, so on compound interest, you're either investing money or you're borrowing them. It works the same. So for a principal P invested at an interest rate R for T years, the new balance A is given by one of these formulas, okay? So the principal is like the money that you initially put in the bank. The interest rate is given as, it's 5% a year or 1.5% a year. So it's like a yearly interest rate. It's usually given as a percentage, but you need to write it as a decimal when you put it in the formula. The length of time that you keep the money in the bank and the interest is applied over that time is given in years, so usually. And you're interested in figuring out A, the new balance. It's like, how much money am I going to have in the bank 5 years from now, 10 years from now, and so on. Okay? So you have two options for equations. A equals P, parentheses, 1 plus R over N, and T. So this you use when its interest is compounded n times a year. So compounded means how many times a year is the interest applied on my account. So you can have like several ways. You can have annually. So it's applied at the end of each year. So n is 1. You can have semi-annually. Twice a year, so n is 2. You could have quarterly, 4 times a year. You can have monthly, at the end of each month, so it's 12 times a year. You can have daily, 365. It's 365, it doesn't care about leap year, right? So these are examples of where this formula, you're going to use this formula. And N tells you how many times a year the interest is compounded. The interest is applied to the money that you have in the bank at that particular moment, at the end of a month or a year or a quarter, so on. This other formula is applied if the interest is compounded continuously. So it's not like every day or year or month, it's every instant, okay? So this one uses that natural base E, and most things in practice are compounding continuously, just because the formula is easier to use. So it's a bit less complex, right? So let's look at this example, and we're going to sort of read through, decide which formula is applicable, and then apply it to get the amounts. All right, so a total of $10,000 was invested in a college fund for a new grandchild. If the interest rate is 5%, how much will be in the account 18 years by each method of compounding? So we're asked to compound quarterly, monthly, continuously. All right, so let's look at this information and see what we're given. So this is P, that's the initial amount. It says interest rate is 5%, so that's R is 5%. You changed it to decimal, divide by 100, you get R is 0.05. And we want to put the money in for 18 years, so T is 18. Right? Part A says we compound quarterly, so that means N equals 4. Compound monthly means N equals 12. And compounding continuously. So this is going to use that first formula. A equals P, 1 plus R over N to the NT. And compounding continuously is going to use the second formula. A equals P e to the RT. Alright, cool. So let's do A. So the amount at the end of 18 years is going to be the $10,000 that's put in. 1 plus R over N, so 0.05 divided by 4, to the 4T, 4 times 18, okay? So basically, you plug this in the calculator. So let me show you a good calculator online. All right, so Desmos scientific calculator is a good one. You can use Google Calculator too, but I like the Desmos one. Okay, so here it is. So I want to do 10,000 parentheses 1 plus 0.05 over 4 to the power 4 times 18. Okay, so 10,000 parentheses 1 plus 0.05 divided by 4, and I'm going to use my arrow, to the power parentheses again 4 times 18. It's important to use the parentheses in the exponent because otherwise you might take that second number to the bottom. Okay, so 24,459.20 cents. Alright, so you want to round to 2 decimal places because it's like dollars and cents. Alright, so that's how much it will be there after 18 years. Alright, part B, it's same formula but compounded monthly, so the n is going to be 12. Okay, so we have, again, 10,000, 1 plus 0.05, but now divided by 12, and the exponent is going to be 12 times 18. Okay, so we're going to go back to our calculator. 10,000 times 1 plus 0.05 divided by 12 to the power 12 times 18. So 24550.08. 24550.08. Right? So they shouldn't be much different because you're working with the same amount of money, with the same interest over the same amount of time. But it's in the second part, in part B, you're applying the interest more often, so you get a little bit more money. Okay? But it's not that much more money. It's almost $100. Okay, but close. Okay. Now C says we want to compound continuously, so we're going to switch to this formula. So A is 10,000 e to the 0.05 times 18. So let's get our calculator. All right. So let me clear this. So the e is found under the functions. You can see e here, either one. So we have 10,000 e to the power parentheses 0.05 times 18. 24596.03. 24596.03. Okay. Okay, you can see the best deal is when it's compounded continuously because the interest is applied like every moment. So that's kind of the most money that you can get if you get your interest compounded continuously. And that's what usually in practice you get. All right, this is applications of exponential functions to financial models.